Hello and welcome to this talk. Thanks for your interest. I will be talking about an event time algorithm for finding Hamilton cycles with high probability. My name is Pascal Su. I'm from ETH Zürich, and this was joint work with Rajko Nenadov and Angelika Steger. So I will be using standard graph terminology. Just for completeness, let's see a Hamilton cycle. Hamilton cycle is a walk on the edges of a graph such that we visit every vertex exactly once and we return to the original vertex, the starting vertex. Finding a Hamilton cycle is a well-known problem in computer science and mathematics, and determining whether one exists is NP hard. Most of the community does not believe that there exists a polynomial time algorithm to find a Hamilton cycle, or even to determine whether one exists in a graph. So in general, this is a hard problem, and we do not expect to find a polynomial time algorithm, but already very early, Dirac found a theorem which said that if every vertex has degree at least n/2, so the min degree is n/2, then the graph must be Hamiltonian. And the way that one way to prove Dirac's theorem is to use pulsar rotations. And pulsar rotations are a very common tool in this area. Very many proofs rely on the fact that we can rotate a path and then try to extend it to a Hamilton cycle. The way this works is if we have a path of some length, and we would like to extend this path, so we would like to make it longer, but it could be that the endpoint of the path no longer has any free edges to unused vertices. Then we can take an edge from this endpoint to any vertex along the path, like this, and we can replace the preceding edge of the vertex with the new edge. And then we get a new path, which covers the same vertex set, but we now have a different endpoint of the path. And we can hope that from this endpoint, we find edges to new vertices, which are currently not in the path. These polarizations can be repeated, and at some point, we hope to find a continuation of the path so that we can extend it to more vertices. There are several different variations of the pulsar rotations. The one we will be using in this talk is the second one here. We use two edges, and the advantage of this pulsar rotation is that the order of all the vertices stays the same. So the predecessor of every vertex, except for this one here and the end vertex, are the same. So in particular, also, if we had directed edges, this would still be a valid new path. All right, so in this talk, I would like to talk mainly about random graphs. In random graphs, we have the random graph model GNP, which is most likely the most well-known and well-studied random graph that we know. And it describes the graph on n vertices where every edge is present with probability p between 0 and 1. Each edge is there independently, and if we take concentration bounds, then also using Dirac's theorem, we immediately see that if p is slightly above 1/2, this graph must be Hamiltonian with high probability, because every vertex with high probability has more than n/2 edges. The question is, of course, is this the best possible? And here I would like to extend a bit on random graphs. We, of course, know the random graph GNP, but there also exist other random graph models such as GNM, which is a uniform graph from all graphs with m edges, or a GNR, which is a R regular graph, again, chosen uniformly from all R regular graphs, or a K-out, which is a graph where we add at every vertex edge chosen uniformly, K edges chosen uniformly at random, deleting multi-edges if we need a simple graph. Or, for example, sometimes we want a property such as the min degree. And for GNP, we can restrict on the minimum degree being at least L. For all of these graph models, we know very precisely where the threshold for Hamiltonicity is. For GNP, the threshold is around log n over n. And we know precisely when the probability tends to 0 and when the probability tends to 1. This threshold actually coincides with the threshold for minimum degree of 2. Should be clear that any vertex with degree 1 cannot be part of a Hamilton cycle, as any vertex in a cycle has degree 2. The same holds for GNM. We know the threshold very precisely, and the threshold again coincides with minimum degree 2 in the graph. Also for GNR, the regular random graph, we know that 3 regular graphs are Hamiltonian with high probability, and 2 regular graphs are not with high probability. The same goes for K outs. There again, 3 outs are Hamiltonian, 2 outs are not. And again, the bottleneck is when 3 vertices of degree 2 share a common neighbor. For conditioning on minimum degree 2, we have also that GNM and also GNP have a threshold for Hamiltonicity, and there are very similar results on various related problems of Hamiltonicity. In random graphs, we can find very many disjoint Hamilton cycles as soon as there exists at least one. We can pack Hamilton cycles, we can find rainbow Hamilton cycles. All these are well-known results and illustrates that on random graphs, it is the problem of determining whether there exists a Hamilton cycle is very different than the general Hamilton cycle problem. So this brings us to our second part, the algorithms. Algorithms for random graphs have been known for a while, and this is just an outtake of a few of them. Already in the year 79, Anglin and Valiant proposed an algorithm with time n log squared n, which works for the random GNP as long as we are a constant factor above the threshold. Later, Shamir and also Bolabas, Fenner, and Friest improved the threshold for which we could determine the existence of Hamilton cycles down to P being exactly the threshold. And there was less a focus on the runtime. This is why the runtimes here are n squared and n to the 4. But these are all polynomial runtimes, which is significant for the P versus NP question. Later, there are results by Gruevich, Schiller, Tomasson, Alon, and Krivelovich, which also showed some improvements there. They actually use the adjacency matrix model, and therefore their times are optimal. And they can show their results down to a P of 1 over square root n. Okay, so there will be a technical detail in this talk, namely that we actually want an O of n time algorithm, but the number of edges in our graphs will be at least n times log n if P is log n over n. So we are not actually allowed to look at all of the edges of the graph. So we assume that the adjacency lists are randomly perturbed and that we can query the next edge at any vertex at constant time. There is a bit of a technical detail to prove that we can also in constant time query a neighbor such that this neighbor is distributed uniformly at random among all neighbors. So if you would like to see the details on this, we would refer to lemma 8 in our paper. So for a start, I would like to explain how the original algorithm of Anglin and Valiant works, because our algorithm works very similarly, besides that we improve upon some of the steps. So the idea is, because in the random graph we have so many Hamilton cycles, we can do a random walk type strategy and hope to succeed anyway. So this means that we can start on a new vertex and then query an edge. And as long as the new vertex is an unvisited vertex, we add this edge to the path we already have. And this works very well at the beginning. We can just add edges as long as there's a linear fraction of unvisited vertices left. We can in constant time query new edges such that we find a new edge to an unvisited vertex. At some point when the path is long enough, we expect to find a lot of edges which connect to vertices which are already part of the path. If the distance of this vertex that we have an edge to is less than n/2 to the end vertex of the path, then we throw away this edge. However, if the distance is at least n/2, then we keep this edge and we replace the preceding edge of that vertex like this. And we detach a cycle, which by definition will have a length at least n/2. This way we get a new endpoint of our path, and from there we can keep on querying. We keep on querying until while we find new unvisited vertices, and if we ever hit a vertex of the cycle again, we can reincorporate the cycle into the path by deleting the preceding edge of that vertex, and then again getting a new endpoint. In this way, any endpoint is with high probability is never endpoint of the path for long. So we never query too many edges from the same vertex. And the probability of hitting a new unvisited vertex is the same as the coupon collector problem. So let us quickly analyze the runtime of this algorithm. We query random edges from every vertex and hope to find all unvisited vertices. This is equivalent to the coupon collector problem, and this will have a runtime of n log n. There is an additional technical detail that whenever we need to detach a cycle and reincorporate it, we will need to do this pulsar rotation, which, due to the nature of the data structure of storing this and updating and maintaining the data structure, this will cost an additional log n factor. And because towards the end of this algorithm, we will need to do pulsar rotations during a constant fraction of the steps, this log n factor really comes into play, and the total runtime is then n log squared n. All right, so we would like to improve upon this, and the first step is that we do is to avoid pulsar rotations, and we do this by, instead of trying to build a Hamilton path, we first try to build a perfect matching. And the advantage of a perfect matching is that any change is only made locally. So if a vertex finds a neighbor which is already in the matching, we can replace the edge with the matching edge, and then continue from the newly unmatched vertex. This way, all changes are made locally, and we don't actually have to store in the database any updates in the rest of the matching. And in a second step, we will make the graph bipartite. This is not actually a necessary step, but I believe it helps in the visualization of how it works. So if we run the same algorithm with bipartite set A and B, let's say we query edges from vertices in B. At the beginning, we expect to often hit unmatched vertices in A, and whenever we do so, we add these edges to the matching. We do this for a while, as long as it is fast enough, and then we will see if we hit from a vertex in B, we hit a already matched vertex in A, we can replace these edges as discussed before, and then query edges from the newly unmatched vertex in B. And if we then hit an unmatched vertex in A, we can simply replace the previously matched edge and in total increase the matching by 1. And so we will call the unmatched vertices in A the target set. The size of this target set will be important for the runtime of the algorithm. For any vertex in B, if we query an edge, the probability that we hit a vertex which is unmatched is exactly the size of this target set divided by the total numbers of vertices in A, which we will call n for now. So the probability of success after a single step is the size of the target set divided by n. And of course, if we consider the random variable of increasing the matching by 1, the time it needs for this will be a geometric series, a geometrically distributed variable with expected length n divided by the target set. And in particular, when the target set becomes very small, this will tend towards n, which is quite long if we want the entire algorithm to run in O of n time. Okay, so to improve upon this, we want to increase the size of the target set. And the way we do this is we expose neighbors of the unmatched vertices and add their matched partners to the target set. So if we have a target set here, we choose an appropriate D and we expose from every vertex here D many neighbors into the set B. These neighbors again are queried such that the vertices are distributed uniformly at random, so we can also expect the size of this neighborhood to be roughly of size D times the target set, as long as the target set is small enough. We will call this the D neighborhood. So for any vertex now in B, if we query the next edge, we will call it a success if we hit a vertex in the target set, or if we hit a matched partner of a vertex in the D neighborhood. Since then, we can simply take the edge to this vertex and the edge from the D neighborhood to the target set and increase the matching by 1. As the picture makes clear, this now greatly improves our probability of success if D is large enough, and especially when the target set is small. So let us analyze the runtime for different Ds. As we said before, if D is 0, then we have the same situation as before, and the expected number of exposed edges from B is exactly equivalent to the coupon collector, which is n over log n. However, if D is of size log n, then we always expect the target size to be roughly of an order of log n larger, which also decreases the random walks by a factor of log n. So we expect to only need linear time to increase all the matching to a perfect matching. However, we should also consider that we need to expose edges from the target set, so from every vertex. And of course, if D is 0, then we do not need to expose any edges. However, if D is log n, then the number of exposed edges becomes n log n, and this actually dominates the runtime of the coupon collector, and therefore this is also not very useful for what we have in mind. So what we need is to find the appropriate D such that both the coupon collector and the edges revealed become linear. And what we do here is we actually take a D which varies as the target set gets smaller. So if we say T is the size of the target set which remains, then we choose D to be the minimum of square root of n over T and log n. So as we see here at the beginning, if T is the entire set of A, then this term becomes 1. So we only expose constantly many neighbors of every vertex. But as T becomes smaller, so as the target set becomes smaller, this will become log n in the end. Namely, as soon as T is n over log squared n. And now if we analyze this, the coupon collector should take time sum of t to n over dt, which if we do the calculations, we can show that this is O of n. But also the number of exposed edges we need will be the sum of the dt's, which also if we do the calculations, we will see this is linear. So in total, we only need linear time. All right, so with this trick, we were able to show that we can find a perfect matching in our random graph in linear time. And what we do now is instead of trying to increase the perfect matching directly, we simply take two perfect matchings. We can take two perfect matchings, make them independent by forgetting the first perfect matching during the algorithm, and then we get a two regular graph. This two regular graph will maybe look like this. We'll have some red edges, some green edges, and they will build cycles or double edges in the graph. And of course, our hope would be that these two perfect matching form a Hamilton cycle, or if not a Hamilton cycle, at least that the number of cycles that they create is not too large. But in fact, it's not so difficult to show that these two perfect matchings, because they are independent, behave exactly like the cycles of a permutation. And it's quite well known that the expected number of cycles in a permutation is theta of log n, and this is also concentrated with high probability. So in the end, we get, after taking two perfect matchings, log n many, or of order log n many cycles, and then these cycles should be much easier to join together to form a Hamilton cycle. We apply the similar trick as before. We expose a neighborhood from one vertex of every cycle. We expose log n many neighbors, and then from the endpoint of the path we currently have, we also expose log n many neighbors. If we can find two adjacent vertices which are in these new neighborhoods, then we can form a new path, which is illustrated in red here, which includes the cycle and keeps most of the path structure the same. And if we do not, we can simply pulse or rotate the entire path and retry with a new endpoint. So there's some technical details how to store the paths and the cycles in a way such that the testing can be done into constant time, and the rotations can be done in log n time. But for this, we can apply AVL trees combined with linked lists. And if you're interested in further details, we would refer to lemma 10 of the paper. Thank you for your attention. If you have any questions, feel free to write an email or ask during the talk.